Okay, so here's the final video of the holidays. This one, a revision really of connected particles, because I just feel that we maybe rushed it a little bit. And the nice thing about this is it allows us to revise a lot of the other stuff that we did involving inclined planes and friction and so on. So I'm in the motorbike book. I'm on page 135. And question 3 is the first of the 3 questions that I want us to look at. So screenshot that if you haven't got your copy of the book. So the thing about connected particles, as you may remember from last year, is that we can view them as separate entities. So we can just think about the car with a tension pulling it up the slope. Or we can think about the truck with a tension holding it back, without really understanding what it is holding it back. We don't need to worry about the fact that that's a car or not. The pulley is not really relevant in this. We're told it's smooth, so there's no energy lost here. Sometimes with connected particles we deal with it as one complete system. Actually, that's less of an issue when you've got situations like this where you've got a slope or and a level bit, or maybe 2 different slopes. But yeah, it's basically always going to be either whole system or one separate or the other separate. So I'm going to draw a sketch of this. I note that the slope is smooth, no friction there, whereas the horizontal area is rough, so there is friction there, and they've already marked that. And the key thing here is that this system is not in equilibrium. This system, the 2 things are moving. So we're not talking about the forces being equal, we're talking about F equals ma here. So the first thing I'm going to do is work out that acceleration. I'm going to draw a quick sketch, come back to you, and we'll work out the acceleration. Okay, so you'll note from my diagram that I haven't even bothered connecting them. I'm dealing with them as 2 separate entities. This is a lot simpler because there's only a couple of forces involved. The angle here is 65 degrees, and because this is a slope, I know that this is best considered by resolving parallel and perpendicular to the slope. A lot more forces going on here. I've got the reaction force and the weight. I've got the driving force of the engine. I've got the tension from the rope, which of course will be the same as the tension here, and I've also got friction, and because it is moving, friction has already reached its maximum value, so I know that F is equal to mu r, and I know what mu is. So let's firstly work out the acceleration. I guess I said, you rarely consider these things as single entities, but I guess this is us considering it as a single entity. So if you read what it says, see if you can suvat it up and get a value of acceleration. Okay, so we're told that it starts from rest, it moves 10 metres in the first 30 seconds. So I used S equals, and I wanted to work out A, so S equals ut plus half at squared, but of course u is 0, so there's no term there, and so I chose to write that as a fraction rather than as a decimal. Okay, so we're now asked to find the tension in the cable or the rope, and as I said, this is quite complicated, lots going on here. This is a little bit simpler, so I'm going to concentrate here, and I've got a choice here of either resolving parallel or perpendicular to the slope. So let's take a punt and go parallel to the slope. So I'm thinking in this direction, and it's not in equilibrium. Remember, it's accelerating. I've got an acceleration of 1 over 45 meters per second squared. So we're dealing with not forces up equal forces down, but whatever the combined force is, it's going to equal mass times acceleration. So the force is up, I've got the tension. Force down, I've got the component of the weight in that direction. So that's 800 g times the cos of 65. and that equals the mass. Mass is 800 times 1 over 45. So we can do some sums there to work out the value of t. Okay, rounded it, but I've also stored the exact value because I may well need it. We're then asked to work out the driving force of the truck. And so we're now looking up here, so I'm not interested in this at all. However, t here is this value here. So for this, I can either resolve vertically or horizontally. I've got a number of unknowns, but don't forget I know a relationship between F and the reaction force here. So I'm hoping that you're going to be able to resolve, so that was for the car. Now for the truck, I'm hoping that you're going to be able to resolve vertically and then use F equals mu r, and then you're going to be able to resolve horizontally to actually answer the question. So have a go and see if you can finish that bit. So resolving vertically, we're not dealing with F equals ma because it's not moving up or down. We've just got forces up equal forces down. So I just know that the reaction force just equals 2000 G. But F is equal to mu r, so that's 0.8 times that. So that gives me a value of F. So I now know T. I worked that out a moment ago. I now know F, that's 1600 G, and I know it's accelerating. So I can now look horizontally and use F equals ma. So I've got the force pushing it forwards, W, take away the tension pulling it back, take away the friction, equals mass times acceleration. I know this, so I can work out W. Okay, we're then told in the final part that the rope snaps. So we no longer have that. But we're told nothing else changes. So I know the friction isn't going to change because that's a relation that's related to that reaction force, and that will only change if the mass of the car changes. So we'll assume that's not happening. And we're told the driving force stays the same. So now we're just looking at this system here, and we're going to look horizontally. I'm going to use F equals ma, and we're going to see what now happens. So now we've got nothing pulling it back. This was my formula for horizontally, but now I've got the driving force. The only thing holding it back is friction, which will still be the same, 1600 G, and that will equal mass times the new acceleration, which is actually what I'm trying to find. So I know W, I know F, I need to work out A. So that's quite a simple sum. See if you can do that. Okay, so I already knew that, but I'd stored the exact value. I'd stored it in memory W, trying to use the right memories. I already knew this, F, and I didn't bother storing that. I just typed it in as 1600 times 9.8. Divide that by 2000 and round it to three significant figures. End of the question, so don't need to store that exact value. Okay, so that's that question. So the next one I'd like to try, same page, still on page 135, but it's question 4. So again, screenshot that if you haven't got a copy of the book. Right, so again, I'm going to go away and draw a sketch of this and come back when you've done the same. So again, I've drawn it as two separate things. So here I've got the block Q. It's being held down, it's got its weight and you've got the tension. Here's the block on the rough plane. So I've got the reaction force, got the weight, got the tension of the rope. This is interesting, isn't it? The direction of friction. So this is holding it in place, this wire here. So the direction this wants to move is down. This is just stopping it move. When it says it's held in limiting equilibrium, you've got to think, okay, what happens if you take that away? Well, it's going to slide down. So friction is going to resist that motion. So friction is actually acting up the slope in this case. And again, I know friction is related to the value of this because it's in limiting equilibrium. Friction is at its maximum value. And so that is 50 degrees there. So we are asked to find the tension in the second string. Now it's not immediately clear to me which I need to work out first, but I do know here I've got two unknowns. So I'm wondering if I'm better off starting here. So here's what I'm going to do. For this block here, I'm going to start by resolving perpendicular to the slope, which means these two forces I don't need to worry about. Then I'm going to use F equals mu r, and then I'm going to resolve parallel to the slope, because by then r won't be an issue. I'll know what F is, and that will allow me to work out T, and then I can come over to this side and work out the value of K, which is what they're after. So I'm going to start on the slope. Okay, so pause and see how far you can get with that. Okay, so resolving perpendicular to the slope, no movement here. So you've just got force up equals force down, and the force down, well, force going that way is 60g times the cos of 50, which I can work out, and then F, this force here, is equal to mu r because we're in limiting equilibrium, so that we're told in the question mu is 0.1. So I get a value of F, which I stored it in my memory F. I then, for the same, still for the slope, resolved parallel to the slope, so I had T and F going up, and 60g cos 40 coming down. I've just worked out what F was, so I could work out T. And then switching to Q, again, it's not moving, still in equilibrium, force up equals the two forces down. I know T, I've just worked it out, stored it in the memory T, so I can work out the value of K. So we're then told that this string is cut. So if we look at the three calculations we've just done, I guess the question is, which of these calculations will need to change? Will this calculation change? Well, it won't, because it is not starting to move up or down in this direction. So this calculation is going to stay the same. So I'm still going to know the value of F. However, these two calculations will change, because these calculations are forces up equal forces down, equilibrium. Whereas what I need to do is now turn them into F equals ma equations, because it's going to start accelerating, and it's going to accelerate in this direction here, isn't it? So for this block, I'm going to have that, take away that, equals mass times acceleration. And this, it's going to be accelerating down this way. So for this block, I'm going to have 60g cos 40, take away t, take away f, equals mass times acceleration. Now, there's a couple of missing values there. There's t and there's a, but of course t will be the same. So see if you can rerun these two calculations, turning them into f equals ma calculations. Once that k has gone, you're going to get simultaneous equations. So see if you can solve those simultaneous equations. Okay, so this becomes this, f equals ma, so you've got the force coming down is the component of the 60g weight, so that's 60g cos 40, and then these two forces going up So take away f, take away t. F is still the same. I've still got it stored in my calculator from the previous calculation. T has changed, so I can't use that stored value. And that equals 60, the mass times acceleration. And I rearrange that as t equals. You may well have solved these simultaneous equations differently. That's the way I'm going to do it. This equation, resolving for q, you've just got t, take away 20g, sorry, not 20q, equals mass times acceleration. And again, I rearrange that as t equals. So I'm then going to work out the value of a. Don't care about t, don't need it, because the question's about how fast it's going in 5 seconds. So I just took my two t equals equations, this one, and made them equal to each other. I added 60a to both sides and took away 20g. Remember, I still know f, so I just whacked that into the calculator and got this value, which I stored in memory A, and then it's just a SUVAT problem, isn't it? So it's accelerating at 2.7 blah, 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 meters per second squared. It's initially at rest, because when you let go of k, it's just at that instance it wasn't moving, and 5 seconds later. So v equals u plus at, but u is 0, 13.5 meters per second. Well done, if you got there. So here is the final question, which I'm not going to work through, but it's on page 136, just over the page, but I am going to post a solution to it along with the video. And of course, you've also got the pretty good work solutions in the back of the book, haven't you? But here we've got two rough slopes. So, and we're told the coefficient of friction is the same in both cases. So it's moving in this direction, so I'm going to have a friction force here resisting that motion, and a friction force here resisting that motion. And I'm going to be able to get an expression for those two friction forces, because resolving perpendicular to the plane, I'm going to be able to work out the value of R and the value of R there, using 5g and 8g, the component of those two forces, and F will be equal to mu times R, because it's moving, F will be at its maximum value. And then hopefully you'll be able to just do parallel to the plane on this side, parallel to the plane on this side, and do a little bit of simultaneous equation work again. You've got T, which is the same on both sides. Remember, this is F equals ma, because it's already moving. There we go. Have a go at that, and I look forward to seeing you all in school next week.